In this example, we have a closed system that is executing a continuous process. So we have a gearbox that is at steady state that is receiving a work input and perhaps reducing the gear ratio of this top shaft to something smaller, so that the input the rotation rate of the input shaft is slower than the rotation rate of the output shaft. But in any case, this gearbox operating at steady state, we know some boundary temperature, we know the box temperature, and we know the input work, and we know the area of the box. So all those three quantities are given to you in the problem statement on your page. And what we're asked to find is the output work of the output shaft. So the input work is going to be given as a negative quantity in kilowatts. That's just to denote that the work is in fact an input. So we expect that the output work is going to have a positive quantity, and we'll want to find that in kilowatts as well. So the first thing I need to do is define my system. So I'm going to just draw a system boundary around my gearbox. Okay. So some other important things to note. So you're given a boundary temperature. You're given the temperature of the environment, or the environmental air, and you're also given this convection coefficient here, H. So I'm going to show you how to use these things to find what the heat transfer is, and it's going to be, of course, away from the box. So when these boxes, they have internal gears that are under friction, so they're going to be creating heat, and at steady state we need to be releasing that heat to the environment. Okay, so the first thing I'm going to do is start with a first law energy balance, but instead of writing it for a process and including delta KE, delta PE, and so on, I'm going to write it as a time rate. So here I've got the time rate of energy contained within my control volume. Of course, dE dt is equal to dKE dt plus dPE dt plus du dt. Now, I don't really care about all these individual forms of energy in this case because I'm at steady state. So I know that dE dt is going to be equal to 0 because I'm at steady state. So instead of writing 0 there, let's write SS to remind ourselves that this quantity is 0 because we're at steady state. And of course that's equal to Q dot minus W dot. Again, the dots are denoting that I've got a time rate of change of, or time rate of heat and work transfer. So now I'm left with Q dot equals W dot. So W dot equal to Q dot, or however you want to write that is fine. This W here, W dot, is going to be W dot 1 plus W dot 2. So again, I know W dot 1. I'm looking for W dot 2. So known and wanted. But I still need to sort out what Q dot is. So in a previous module, you found that, or you were told that the rate of heat transfer by convection is equal to minus HA, in this case TB, the temperature of my surface, minus T infinity. So I know H, that's given up top, 0.2 kilowatts per meter squared times Kelvin. So here, if I plug in that value and multiply it times meters squared and a temperature change in Kelvin, then my heat transfer is going to have units of kilowatts. And of course, here I've got a heat transfer coefficient that is a positive value. an area that is a positive value, and then of course this delta t is going to be a positive value as well. So because of this negative sign out front, I do expect my quantity for Q dot to be negative something kilowatts, which makes sense because I've got heat leaving the system. Okay, so now it's your turn to calculate Q dot for yourself using the variables given in your problem statement.